Hey friends, Dr. Borole is here. Today we will see how the electronics is evolved. The electronics starts with the vacuum tube. By Mr. Fleming in 1997, the vacuum tubes were invented. The vacuum tubes are shown in the figure. Their dimensions are quite big. It consists of anode, cathode, and great type of electrodes. The sizes are ranging from 1 to 1.5 inch in diameter to 2 inch to 4 inch height. These devices work like a diode and transistor, but these are all mechanical grid devices in which there is a cathode, which is a thermionic cathode, which emits the electron whenever the cathode is heated. When anode is kept at positive potential, the electron gas created around the cathode, which is now moving towards the anode, and the flow of current will be established. Whereas when the third electrode grid is added, it's called control grid. Normally it is kept at negative potential. This negative potential intensity will decide how much electrons will be transferred from cathode to anode, and hence the flow of current. Larger the negative potential at grid, smaller will be the current flowing from cathode to anode. Thus, the conventional current is flowing from anode to cathode, right? So here, these devices leads to the applications. Those are quite heavy and bulky. The vacuum tube triodes are used as amplifying devices by Lee D. Forest. The triode and tetrode and pentode devices, those are coming until 1940s. BJT were invented in 1948 and they uses germanium and silicon as a semiconductor. Junction field effect transistors and MOSFETs were invented during 1951 to 58, but their practical applications and use started around 1970. The integrated circuits, those are the circuit on semiconductor wafer, also called as ICs. They will start developing in 1975 onward. ICs are of two type, analog ICs and digital ICs. Analog ICs uses two type of technologies, bipolar junction transistors and MOSFET for their development of the circuitry on the wafer. The bipolar junction transistor chips are called as bipolar chips. MOSFET chips are called as MOS or CMOS chips, and the chips which use the combinational use of BJT and MOSFET is called as BiFET technology. Typical example of integrated circuit, those process the analog signals are op amps, ADCs, and DACs. Op amp is a operational amplifier. ADC stands for analog to digital converter, and DAC stands for digital to analog converter, and etc. Typical IC packages are shown in figure. When the circuit on chip is small, few pins are required. So pins are arranged on both the sides of the IC package. These package is called as dual inline package. The dual inline package are available with larger number of pins also, shown in figure 2 and figure 3 here. That is HDIP and SDIP packages shown here. Whereas when pins are more, the pins are arranged on all edges of the package called quad inline package. Whereas when the circuit is very big and requires more interconnection to the external component, then the pins are arranged on one side of the IC in a concentric squares as shown in the figure as CPGA. Whereas some of the ICs nowadays they can have a pins like QFP. These devices doesn't have through hole pins. They are folded and they will be soldered on a single side of the PCB. These are also called as SMD devices, that is surface mount devices. Those are used nowadays in electronic circuits and boards. The digital families are RTL for register transistor logic, DTL for diode transistor logic, TTL for transistor logic, ECL for emitter coupled logic, and I square L, that is integrated injection logic. These families uses the component like resistors and transistors only in developing the digital integrated circuit. Whereas in TTL family, the devices used are the bipolar junction transistors only. And that's why the name given to the technology. RTL was the old family, TTL still in use, ECL and I square L is also in use. Whereas current generation technology that uses the MOSFET as a building block of integrated circuit, the N type of MOSFET and P type of MOSFET forms PMOS and NMOS technology devices. Whereas when both are used in a basic cell of the digital gate, then it is called CMOS. The technology used for fabricating the digital integrated circuit or analog integrated circuit that will start from small scale integration system to ultra large scale integration system. Depending on the size and complexity of the electronic circuit to be fabricated on chip, the technology evolved from SSI, that is called small scale integration, MSI, medium scale integration, and LSI, large scale integration. Whereas very big devices like microprocessor and microcomputers and the complex circuitry that can be developed using the technology called VLSI, very large scale integration systems, and ultra large scale integration technology. The IC technology evolved from 1971 to 1924 as shown in the table. In 1971, our technology have a limitation to miniaturize the devices on the chip. In 1971, the technology was 10 micrometer technology, which means that our technology is capable of fabricating the devices as small as 10 micrometer in area. Whereas in 1984, the technology is evolved and we can get the capacity up to 1 micrometer in fabrication. Whereas in 1996, we were capable of fabricating 250 nanometer devices on a chip. Whereas in 2014, our technology is evolved and make it possible to fabricate the devices around 14 nanometer. In 2018, we reached to 7 nanometer small device fabrication. In 2024, the technology is so evolved that we are capable of developing the devices in the range of 2 to 4 nanometer in size. Since the device sizes are very small nowadays, the IC technology can then capable of fabricating millions and billions of devices on a small chip. The electronics were used from the historical age of 1844 to the current age of technology. 1844, the Morse in 1844, the Morse invented telegraph system where comes in picture, whereas telephone was invented by Bell Laboratories in 1976. In 1901, the Marconi has made first radio transmission device. Television was first invented in 1923, whereas in India, the first application of television we found in the era of 1970 onward. 1940 to 45, the radar development and invention in radar systems are on peak. In 1998, the high definition television systems were in the market. And today we are having very fast communication devices like mobile phone. And we have the computers and computer communication system nowadays. Those are few applications of electronics. What is the impact of electronic development on industry? Let us see. Obviously, speed of development is increased due to the development and use of electronics. Quality of production is improved. The scale of production is improved. That is mass production of the components as well as the applications are possible, which reduces the cost of the equipments and electronic systems. Use of electronic system reduces the human efforts in manufacturing also. Production automation is possible because of electronic systems, which reduces the human efforts, and larger production rate is getting possible with better quality. That leads to higher efficiency in production. If you see the impact on the society by the use of electronics in the society, that makes the human life easier. The operations day to day life are becoming simple and easy. Reduction in labor involved in various works. Time saving is possible. Luxury and ease of living is improved for the people. Electronic found in various applications are listed here. Electronics is used in industrial manufacturing applications, automobile shipping, aviation and traction applications, defense application and radar and satellites, medical sciences and the equipment in the instrumentation and automation systems. The electronics is used in communication and social media and entertainment industry also. And you will find that no area remains untouched where the electronic doesn't involve. Now, if you see the current art of technology where we are currently in the era of artificial intelligence and machine learning. This AI and ML used today even in the consumer electronic devices like smart home devices and smartphones, automobile systems, healthcare system, voice and image processing. The second era is Internet of Things, IoT. IoT is mostly used for smart homes, wearable devices, area monitoring and data acquisition, etc. IoT is used everywhere and it used the internet as a backbone and the devices called things, they are connected to form the application over the small area or the big area throughout the world. Current technology we are working with is a 5G technology having following advantages. It can transfer the data faster and with low latency. That is the waiting time. So data will be transferred with low waiting time. And 5G technology have the major advantage of improved connectivity. Currently, we are in the era of sixth generation technology, and the development is going on in the world on seventh and 10th generation technology. The electronics is currently used in wearable and flexible electronic systems also. Nowadays, flexible displays are available, and on wearables also the electronic systems are used. The sustainable and eco-friendly electronics, that is the era where electronics is used in renewable energy, in recycled material, reducing the carbon emission, etc. The organic electronic display, photovoltaic cell, solar power system, and energy efficient lighting are using electronic system nowadays. In green manufacturing, which uses the renewable energy sources to reduce the consumption of energy and minimizes the waste in the production. For that purpose also electronics is used. Currently we are researching in the quantum computing, that is altogether the research topic. Electronics is used today in AR and VR systems, that is augmented reality and virtual reality systems, mostly used in gaming. Electronics is used in electronic vehicle also. The electronic vehicles Those are controlled from battery with the electronic controller, and it is efficiently controlling the power flow, and it is environmental free also. The noise generated by electronic vehicle is less. The engine concept is altogether dropped in EVs. They uses the electrical motors, power controllers, and powering batteries. All these things are controlled via the electronic controller. Currently, electronics is used in advanced display technologies, and it is used in cyber security system also. Let us focus on the various electronic components. The electronic components are classified in two broad groups: active component and passive component. The passive components are the resistors, capacitors, and inductors. The active components are the electronic tube and semiconductor devices. We will see more details of differences and similarities in active and passive components in the next part of our lecture. The semiconductor devices can be a p-n junction diode, transistors, and FETs. So all of the semiconductor devices comes under active components. Let us see the comparison of active and passive component on various bases. On the basis of nature of the source, the active components are the components those delivers powers or energy to the circuits, whereas passive components are the components which utilizes the power or energy from the circuit. Typical examples of active components are diode, transistors, SCR, integrated circuit, DC generators, current and voltage sources. Whereas passive components are resistance, capacitance, and inductors. On the operational basis of the component, if you see active and passive components, the active devices which produces the energy in the form of voltage and current comes under active component. The devices which stores the energy in the form of voltage and current comes under passive components. Some of the devices like capacitor and inductor, those stores the energy, whereas resistance doesn't store the energy. The active component mostly providing the power gain, whereas passive components are not capable of providing the power gain. Active components can control the flow of current under the control of some signal. Like in BJT, the base current is controlling the collector current. In passive components, they cannot control the flow of current under any control of the signal. From the external source requirement point of view, active components requires the external source for their operation, whereas passive component doesn't require any external source for its operation. From the basis of nature of energy point of view, the active components are energy donors and passive components are energy acceptors. Let us see the passive component first. The first component is resistor. Resistor is a device which is based on the property of material called resistance. Resistance is defined as opposition to flow of current. The symbol of the resistance is shown here. The first symbol is for fixed resistance and second symbol with the arrow is a variable resistance. The arrow terminal indicates the variable terminal, whereas two extreme terminals, those are the terminals in which the resistance is always fixed. Whereas in variable resistance, one fixed terminal and a variable terminal, the resistance will change when the wiper arrow is changed. The units of resistance is ohm that can be measured in ohm or milliohm or kilo ohm or mega ohm and so on. The resistance of a material is given by the formula R is equal to rho L by A, where rho is the resistivity of the material, L is the length of the material or conductor used to implement the resistance, and A is the cross sectional area. So we observe that the resistance is increased with L and decreased with the increase in area of cross section, area of the specimen. Whereas the selection of material, that is rho, is also decides the resistance. This equation says that resistance is proportional to the length as well as rho of the material and inversely proportional to the area of cross section of the material. Resistors are classified in various groups. They are basically linear resistors or non-linear resistors. The linear resistors are normally implemented by using metal composition material. They can be fixed resistors or variable resistances. A typical fixed resistances are made up from carbon composition, or it can be a wire wound type of resistances, or it can be the metal film resistances. The variable resistors are either potentiometers, trimmers, or rheostats. All these are having three terminals, two fixed and one variable. And there is a mechanical arrangement so that the user can change the resistance between one of the fixed terminal and a variable terminal. Non-linear resistors, on the other hand, those are mostly made up of semiconductor material. The typical examples are thermistors, those are thermal resistors, LDRs, those are light dependent resistors, and VDR, those are voltage dependent resistors. You are going to use these components in your electronic journey. General specification of the resistors includes the maximum voltage and maximum current ratings. That is Imax and Vmax. Maximum power ratings P or P max is given by I square R, or it can be V square by R, or it can be V into I. And power is normally mentioned in watts. The resistors are available in practice in various power ratings. Those are 1/4 watt resistance or 1/2 watt resistance, 1 watt, 2 watt, 5 watt, and 10 watt, etc. are available in the market. Larger the power handling capacity, larger the physical size of the resistors. The resistance values and the tolerances, those are marked on the devices, are shown here in the figure. The resistances, considering say linear resistances, they are made up of a composition of materials. Those are mixtures of metal or alloys. They consist of two connections for making the electrical connections and coated with a insulating material. And the body is having the color code in the form of color rings as shown. The resistances are available in 4 band, 5 band, and 6 band color coding. Whereas if you see the value of the resistance is accommodated in the left side group of color bands, and the extreme end color bands, those are used for the other properties like tolerance and temperature coefficients. The colors in the color code are marked from 0 to 9, that is from black to white. If you see the color sequence, black, brown, red, orange, yellow, green, blue, violet, gray, and white, they have assigned the number 0 to 9. When the color strip is in the first digit position, you can take the color code from this color chart. Now, for example, if you see this 4 band resistance, here first ring is brown, that is digit 1. Second ring is red, that is number 2. Third ring is a multiplier, that is green here, and green have a multiplier 5. So 5 here is a 10 raised to 5 basically. So multiplier is expressed as a power of 10. And therefore, brown, red, green color code combination gives 12 into 10 raised to 5 ohm resistance. That is 1200 kilo ohm resistance. Whereas the remote ring on the other end is golden, and golden stands for the tolerance of plus minus 5%. Here, tolerance is nothing but the value deviation from the value given in the color code. So, for example, if the color code says that it is a 100 ohm resistance and it is having plus minus 5% tolerance, then the value of that resistance may be in the range of 95 ohm to 105 ohm. That is 5%. Similarly, there are 5 band resistances and 6 band resistances. In these 5 band or 6 band resistance or multi band resistances, the last ring of the value group is always the multiplier, and remaining rings are the digits in sequence. For example, in 5 band resistance here, first ring is brown, that is corresponds to number 1. Then black and then black. Black corresponds to 0. So 1, 0, 0. And the last ring is a multiplier with 10 raised to power. Here, the last ring is red. So it is corresponds to number 2. And therefore, the multiplier is 10 raised to 2. And the tolerance ring is brown. Here brown corresponds to plus minus 1%. So this is the resistance 100 into 10 raised to 2, that is 10 kilo ohm with plus or minus 1% tolerance. Sometimes in the property group, there is an additional ring that indicates the tolerance as shown in the 6-band resistor, the last ring. Here this last ring is black, and black corresponds to the temperature coefficient of 250 ppm per Kelvin. The various types of resistor we have seen in the classification. Here the fixed type of resistors are shown. They are classified as carbon composition resistance, wire wound resistance, and film type of resistance. Their construction and the internal cross sections are shown. Here the carbon composition resistance consists of carbon composition material to provide the resistance, and it is coated with a insulating material so that it will be protected from the electrical short circuit. Whereas metal film resistors uses the film of metal, that is a strip of metal wound on the former to provide the resistance. It is also enclosed in a protective jacket called body of the resistor. Whereas if the metal or resistive metal wire is used for forming a resistance, it is normally wound on the insulating former and the two terminals are taken out. It is a wire wound resistance. Sometimes the high power resistances are also covered inside a metallic enclosure called heatsink so that the power lost in the resistance can be easily removed from the element to the environment. The very high power resistance shown in this figure, a wire wound resistance, in which the wire is wound on a insulating former and the mechanical arrangement is provided to make the connection. The variable resistors, again, they are carbon potentiometers or wide wound potentiometers or trimmer. The figure here shows the big size, high power variable resistance consisting of three terminals here. This is fixed terminal 1, this is fixed terminal 2, and this wiper which is moving on the wound wire between the fixed terminal, that is a variable terminal. And here the connection is provided to make the connection with the variable terminal. Whereas the carbon film potentiometers are looking like shown in the first figure. Here between the two fixed end, the carbon film is used on which the wiper is moving and the wiper is connected to the variable terminal. Whereas wire wound resistances in which on an insulating former, the wire will be wound and fixed between the two end fixed terminals. And the wiper is mechanically allowed to move from one fixed end to another fixed end by using a mechanical shaft. So that by adjusting the mechanical shaft, we can adjust the position of the wiper and hence the resistance between one of the fixed terminal and the wiper. This assembly is enclosed in a casing and that look like as shown here as wire wound resistances. Whereas here the symbol of a variable resistance is shown. It consists of two fixed terminals, say 1 and 3, and terminal 2 is a variable terminal. The small size variable resistances Those are available for directly fabricating on PCB are shown here in the figure as presets and trim pots. Their sizes are very small, as shown in the figure here. Just 1 centimeter by 1 centimeter trim pot is available, or even smaller than that is available, and they are normally having the screw arrangement to change the resistance. They are normally developed for calibration type of applications where the adjustment is not required frequently. The second component is a capacitor. If you see the construction of a capacitor here shown in the figure, it is a parallel plate capacitor. Two metal plate separated with the dielectric. The area of the metallic plate is A and distance of the separation between the plate is D. That is nothing but the thickness of the dielectric. The capacitance of such parallel plate capacitance is given by the equation C is equal to epsilon A by D, and it is measured in the units farad. Farad is very big unit, whereas the smaller unit like picofarad, nanofarad, microfarad, millifarad that can be used. Whereas millifarad and farads, these units are mostly not useful for practical applications because these are very big units. Capacitors are mostly available from few picofarads to thousands of microfarads. The symbol of the capacitor is shown here. The first symbol is for non-polarized capacitor, and second symbol here is used to indicate the polarized capacitor. In non-polarized capacitor, the capacitor terminals are interchangeable in the circuit, whereas in polarized capacitors, the polarity is marked on the capacitor. Here, positive terminal of the capacitor is always connected to the higher potential compared to the lower terminal in the circuit. Reverse connecting the polarized capacitor may damage the capacitor. Typically, for large capacitor manufacturing, the parallel plates of the capacitor, those are wound in the form of cylindrical roll shown here and enclosed in a metallic enclosure so that large area can be encompassed in a smaller volume. Such type of capacitors are mostly the electrolytic capacitor. They look like shown in the figure here from outside, whereas the parallel plate capacitor, literally using parallel plates with insulator, is shown here. That is one of the capacitor type that is called as ceramic disc capacitor. So two discs here are separated with the ceramic material, and then total assembly is enclosed inside the protective coating. The capacitors can be available as fixed value capacitor or variable capacitor. Mostly you will find the applications of the capacitor as fixed capacitor. The various capacitor shown here, they looks like as shown in the figure. The variable capacitor is also shown. It is having the variable arrangement mechanically made so that the overlapping area of the two parallel plate can be changed by mechanical arrangement so that the capacitance can be changed. The various types of capacitor listed here are ceramic capacitors, film capacitors, power film capacitors, electrolytic capacitors, ceramic capacitors, film capacitors, power capacitors, and electrolytic capacitors. These types are mostly indicating the type of insulating material used as an insulator or dielectric in the capacitor making. Whereas nowadays the technology reaches to the level where through hole capacitors are not usable since we are using multi-layer boards, and therefore the SMD surface mount technology devices are currently in use, like the circuits of microcomputer motherboards, mobile phones. Those are shown here in the figure. Here, these resistance and capacitances and inductances are called as chip components. Whereas the component values are directly printed on these resistances, either as the coded number or directly in the form of resistance value. A typical SMD chip capacitor is shown in this figure. The color coding of the capacitor follows the same color rule for the resistance what we have seen. Here first, second and third ring, those are accommodating the values of the capacitance. First digit and second digit is a value and third ring indicates the multiplier, that is 10 raised to power. And the value accommodated in these first three ring indicate the value in picofarad here. The next thing is the tolerance and voltage. But nowadays you will find such color coded capacitors are not in the market. Instead, they are printing the numbers of the code directly on the capacitor. Here, if you see here, the number printed is 683J, whereas 6 is the first number, 8 is the second digit, and 3 is the third digit, that is the multiplier, that is 10 raised to power 3. So this capacitor is 68 into 10 raised to 3 picofarad, means 68 picofarad. And code J indicates the tolerance. Here in this second figure, you will see the ceramic capacitor, disc capacitor ranging from 10 picofarad to 100,000 picofarad, and corresponding color, the code is shown here 100. That is 10 into 10 raised to 0 pf. Whereas here last capacitor 104, that is 10 into 10 raised to 4 picofarad. The mechanical variable capacitor is shown here with the details you will observe in the figure. It consists of a mechanical assembly. There is one shaft on which there are set of plates, those are welded. And there is a assembly in which fixed plate are welded. And these plates are arranged such that they can move inside one another without touching to each other. The separating media is mostly air. So air is used as a dielectric here. Whenever you rotate the shaft, the overlapping portion will change, and ultimately the capacitance of the capacitor will be changed. Such multiple assemblies can be installed on a single shaft. So here in the figure shown as air gang capacitor, here the three capacitors, variable capacitor assemblies are installed on the same shaft. So by a single mechanical arrangement called gang arrangement, you can change the values of the three capacitors. The symbol of variable capacitors are shown here. The variable capacitors were found the application in variable frequency oscillators, and signal generators to change the frequency generated by these devices. They found the application in radio receivers as tuning capacitors. They also found in the TV receivers to tune the TV channels. They also found the application in tuned amplifiers. Nowadays, these variable condensers are replaced by electronic arrangement so that you can tune the TV receivers and radio receivers from the remote control device itself. They are mostly using voltage controlled variable capacitances. The next component is the inductor. Inductor is a component based on the property inductance of the material. And inductance is nothing but opposition to the flow of AC current. Inductance is measured in henries. The smaller unit is picohenry and higher unit is henry. The inductance is given by the formula that is N square A mu upon L, where L is the inductance shown here. N is the number of turns used for making that inductor. A is the area of cross section of the core on which the inductance wire is wound. Mu is the permeability of the material used for core, and L is the length of the magnetic circuit. This small l is the length of magnetic circuit, and capital L on the left hand side indicates the inductance offered by the assembly. So we see that the inductance can be increased by increasing the value of number of turns, area of cross section of the core or permeability of the core, or it is inversely proportional to the length of the magnetic circuit. Inductors are broadly classified in two groups: fixed inductors and variable inductors. These fixed inductors, depending on the core used, they can be air cored or it is a cored inductor using specific material like iron core or ferrite cores. Many different materials are also used. Those are mostly the magnetic material for implementation of core for the inductor. The variable inductors are the slack type of inductor called tuned inductor or tapped inductor. The fixed inductors can be air core inductor or iron core inductor or ferrite core inductors. The symbol of the inductor used in the literature are shown here. Here the core inductor is shown. The two parallel line indicates the core. Whereas the fixed inductor with air as a core is shown here in the second figure. Whereas the variable inductor consists of two fixed terminal and variable terminal shown by arrow. Sometimes this another symbol of variac is used as a variable resistance. And tapped inductors have multiple taps. So in various taps, the inductor between the tap point and the extreme fixed terminal point will be changed, and that is fixed between the tap point and extreme end points. So here in the tapped inductor, the value of the inductor can be changed in steps by changing the tap. How they look like physically as shown in the following figure. It consists of a insulated wire, normally enamel insulated wire, which is wound in terms of number of turns, and wire ends are available for connection. Here in the first figure, no core is used, or you can say air is used as a core, therefore it is a air core inductor. In second figure, you will see the wire is wound on a core that is a iron core, whereas wire is wound on the bobbin and core is inserted inside the bobbin. Here in the third figure, the ferrite core that is in the form of toroid is shown, and on this toroid, the insulating wire is wound and two ends are taken out. Similarly, in the variable inductor, you will see it is like a rheostat again, but here the property used is inductor. This is a highly conducting wire instead of a resistance wire, and this conducting wire number of turns between the fixed terminal and the wiper decides the inductance between fixed terminal and wiper. Whereas a ceramic chip inductor is shown in this figure, in which the multi-layer inductor is manufactured and enclosed in the ceramic enclosure. The application of inductor includes the various areas. They are used in power supply mostly, and they are very important elements of filter circuit. Those are frequency filters. They also used in oscillators and tuned amplifier circuits and radio frequency circuit as a filter. Inductor are also used as impedance matching devices. And these inductors are used in wireless applications for filtering elements. Let us see now the active devices. The active devices mostly includes the semiconductor devices and various generators which delivers the power for voltage sources and current sources. We will see here the PN junction diode. The PN junction diode construction is shown in the figure. It consists of a P-type material bar and N-type of material bar sandwiched together, and a metallic electrode anode is connected to the P-type material, and a copper metallic electrode connected to N-type material that is called cathode. The symbol of the diode is shown here. The symbol indicates the direction of current, that is from anode to cathode. That is the meaning of the triangle shown here. Typical practical diode look like as shown in the figure 2.5.2. Whereas on the physical diode, there is a silver ring on one of the bar. There is a silver ring on cathode terminal. So wherever there is a bar, that electrode is a cathode. The details of the PN junction construction, its operation, and related semiconductor physics will be studied under the next topic of PN junction diode. Let us just see various types of diodes. Those are used in practice. A simple PN junction diode, normally called rectifier diode, which is used for rectification purpose. Second type of diode is a light emitting diode called LED. This diode is capable of emitting the light when forward bias is applied to it, that is, anode is kept positive with respect to cathode. And this light emitting capability the diode gets because a special material is used for the construction, which is capable of emitting light when the excitation current flows through the PN junction. Laser diode. Laser diode is similar to light emitting diode, which is made up of a special material. But this material is such that when this diode is forward biased, it emits the radiations in the range of laser frequency spectrum. Avalanche diode, these are breakdown diodes. These diodes have a precise doping level so that they can be working in the avalanche mode or breakdown mode to regulate the voltage across it. Similarly, there is a diode called Zener diode. It is similar to the avalanche diode, but it utilizes the effect of Zener breakdown. Normally, the doping level is controlled so that the Zener effect takes place in the diode under the breakdown region. Normally, avalanche diode and Zener diodes, those are operated in reverse breakdown region. In the forward bias region, these two diodes behave similar to a PN junction diode. Schottky barrier diode is a diode which is having the interface with the metal and semiconductor, and therefore the forward cut-in voltage of the diode will be reduced and speed of the diode will be increased. Photodiode is a diode in which when the light falls on this PN junction, it generates the carrier. So light photons generate the minority carrier around the PN junction. Photodiodes are normally operated in reverse bias. In forward bias case, they are similar to a ordinary PN junction. Photodiode utilizes the special photosensitive material which can convert the light photons to a minority charge carriers. The symbols of various diodes are shown here. First is a rectifier diode or conventional ordinary diode, whereas second is a LED in which the light arrows are shown here that indicates the light is coming out from the diode whenever it is in forward bias. Third is a photodiode in which light is going inside and that generates the current proportional to the intensity of a light radiations. Laser diode, it is similar to LED, it emits the light, but this diode emits the radiation in the laser spectrum of a electromagnetic spectrum. The symbol of the laser diode is shown here with the additional line. Zener diode is shown in the figure here that have a symbol with cathode terminal is slightly folded back. Schottky barrier diode symbol is also shown, whereas another type of diode not listed above is called varactor diode. This diode is normally provide a variable capacitance across it whenever it is operated in reverse bias. The VI characteristic of a PN junction diode are shown in the figure. Here in the first quadrant, it is forward bias, that is anode is positive with respect to cathode. The voltage between anode to cathode is called as forward voltage and that is plotted on x-axis. Whereas the corresponding current will be plotted on y-axis. That current is called forward current. We will see in first quadrant Whenever we start increasing the forward voltage across the diode, initially the current is not increasing. It remains around zero. Whenever the certain voltage called cut-in voltage reaches, that is around 0.69 volt for silicon and zero point 0.3 volt for germanium, the PN junction start conducting. The charge carrier injection takes place from anode area, that is P material, to N material, and vice versa, and the current start flowing across the junction. If we increase further the forward voltage, the current is increasing. This relationship after cut-in voltage is exponential in nature. We will see the details of this relationship in the next sessions. This relationship is also called as Shockley relationship for the PN junction. Now, if you see the third quadrant, here we will apply the reverse voltage across the PN junction, that is negative x-axis. We are making anode negative with respect to cathode. And we observe that due to reverse bias, there is no charge carriers available and therefore no current flows. But since at room temperature, some of the minority charge carriers are present, those are generated due to the thermal agitation or room temperature. This very small amount of charge carriers leads to very small amount of current during reverse bias also. That is called as reverse leakage current. The reverse leakage current is in the range of fraction or of nanoampere to few nanoampere. When you go on increasing the reverse voltage between anode and cathode, the current remains mostly a reverse leakage current. For ideal diode, if you go on increasing the voltage up to infinity, the diode will not conduct heavily in the reverse direction. Whereas the practical devices or practical diodes have limited amount of reverse breakdown voltage. Whenever our anode to cathode voltage, that is the reverse voltage, exceeds the breakdown voltage of the diode or reverse breakdown voltage of the diode start conducting heavily due to either Zener breakdown or avalanche breakdown. And suddenly large current flows through the diode and voltage across the diode remains the reverse breakdown voltage. During this portion shown here, after this knee point, the voltage across the diode is large as well as current is very large. And therefore, total power loss across the device is very high. That is voltage into current. And therefore, this very large power device may damage the device in reverse breakdown region for the ordinary diodes. And therefore, care has to be taken that the reverse voltage applied across the diode should not exceed the reverse breakdown voltage of the practical diode under consideration. So these are the characteristics shown, also called as VI characteristic of the diode, since it is the relationship between voltage and current through the diode during forward bias and during reverse bias conditions. Now let us see the applications of the diode. The diode can be used as a rectifier. Diode can be used in the clipping circuits and clamping circuits. Diodes can be used in the logic gates implementation, and diodes can be used for protecting the reverse current. Since diode conducts in forward direction only, if we insert a diode in series of any current path, it will not allow the reverse voltage to be applied to the circuit because it automatically goes in the open circuit state and thus protecting the circuitry further from the reverse voltage applications or reverse current. A typical diodes, practical diodes, those are looking like as shown in the figure. Here you will see the photodiode? It consists of a glass window via which the external light can go inside. One terminal is anode, one terminal is cathode. Whereas light emitting diode, you will see, which is having a glass window from which light is coming out whenever it is forward bias. Ordinary diode, it consists of a cylindrical shape with cathode mark on the cathode terminal with a silver color. Whereas laser diode is similar to a light emitting diode. Here there is a window from which the generated laser light is coming out. Now next device is a transistor. Transistor is basically a trans resistor device and it is a three terminal device. There are two types of transistor we are mostly studying in electronics. One is BJT called bipolar junction transistor and it is having two types, NPN transistor and PNP transistor. And in the MOS technology, the another device is MOSFET. It is metal oxide semiconductor field effect transistor. This MOSFET works on the effect of field generated at the gate to source or gate terminal, and therefore it works on controlling the drain current by the field effect, therefore the name given field effect transistor. Since its construction shows that it uses the interface between gate and substrate, which is formed of metal oxide and semiconductor interface, and that's why the name metal oxide semiconductor field effect transistor. We will see the details of the MOSFET also while we are going to study further the transistors in the next sessions. There are two types of MOSFET exist. One is P channel MOSFET and another is N channel MOSFET. Typical transistors are available in various packages. Here package TO92A is shown and TO220 package is shown. Whereas TO92A is a low power package, whereas TO220 package is a high power package. This another figure shows a cross-sectional view in which how the transistor actually packed inside the enclosure, that is body of the transistor. Here inside you will see a PNP or NPN structure and the leads are connected from these areas to the pins. The back terminal here, that is a heat sink on which the internal vapor is mounted. Normally it is connected to the collector terminal so that heat removal can be faster from internal transistor chip device to the body. The another packages are also shown. Here TO3 package is a metallic package and it is higher power package than even 220 package. Whereas surface mount device package is also shown here in the diagram called SMDs. So we will stop here, friends. We complete the evolution and various devices in electronics. We will see the devices further in detail in the next subsequent session. Till then, bye bye. Have a nice day.